Okay, excellent. Then welcome everyone for today's workshop. My name is Matthias Markowski. I'm a scientific co-worker and protocol writing expert. No, not really, at the Otto von Guericke University of Magdeburg in Germany. I say hello to the 8 people in the room, if I count correctly. And there are also already 5 people connected online, so also welcome to you. And with this, I will also directly share my screen and go to my slides. Yeah, so the idea for today is to explain a little bit what to care about when writing protocols. And before we actually really start, I've prepared a short survey. Hello, hello, come in. Hello. So students in a room are now 12. So I would appreciate if you can go to this website. I think there will be also a QR code in a second, and answer this question: how many protocols have you written so far in your life? We also see the results from previous workshops like this, and I think probably 45 seconds should be enough to answer this question. And there is the QR code. So I would be interested in knowing how many protocols have you written so far. I know that we have some master students here from electrical engineering and information technology, some master students from mechatronics, where I expect that, because it's a German study course, that you have already written lots of protocols in your bachelor studies. And I don't know the other students that we have here, but there's unfortunately, I think, not so much time left because it's already red. Okay, but there we have some results. So I think now we have to look at the blue bars. The light blue ones are the ones from a previous workshop. So most of the people say none. Some say a few or one, and yeah, I think these are the 2 mechatronics students, probably that say much more than 10 because we have already. So the question is, why are you here in this workshop?
For the bachelor.
Okay, okay. Excellent. Yeah, so then I think I don't have my usual disclaimer slide, but the disclaimer or the organizational matters is if you want to have the slides afterwards, you can have them. I will somewhere post them, or you can just send me an email. I will maybe post them somewhere on social media. Then I will try to do a recording. You never know if it works, but I have a camera, I have a microphone. There's a live stream. There are still 4 people watching online. Write something nice in the chat. So hopefully there will also be a recording. And if you have questions in between, feel free to ask these questions in between. Hopefully we will also have some time towards the end to ask questions. If you want to ask questions in German, feel free to ask questions in German. I will translate them, try to translate them to my best knowledge also into English for our international students. Okay. So I will give a short motivation why it's, from my point of view, interesting to write protocols. And then we will have a look on how to write it. And I've separated the section a little bit into content and style, because I think these are 2 separate parts. Then we'll have a look, and this is probably from my point of view, the most interesting part. Take a look at some examples according to this Western movie, The Good, the Bad, and the Ugly, you know. And so we will take a look at, of course, at some not so good examples, and then try to discuss options for improvement. And then I would like to give some tips or some hints for LaTeX. I know that the introduction into LaTeX workshop is, I think, happening in just 1 week. Yeah, so still I think these examples should be understandable, maybe also without having too much knowledge of LaTeX. And at the end, of course, there will be a summary. Okay, so the motivation is, yeah, if you study, you have laboratory internships, you need to write protocols like the mechatronics students. Then if you are working towards the end of your study, if you're writing a degree thesis, bachelor thesis or master thesis, it's also more or less some kind of a longer protocol. You write down what you have done and try to make it understandable for other persons. And if you're working as an engineer somewhere, you also often do measurements, you do simulations, stuff like this, you do research, and you need to report on these measurements, for example. And so the general idea of a protocol is if someone was not present at the day of the experiment, still from the protocol, the person should get an idea what you have done, what you have measured, what you have simulated, what you have experimented, what was the setup, and so on. What were the results that came out of this measurement, and what is, let's say, the further knowledge that someone can get from these experiments? What is the outcome? What does or what do these results mean? Is it good? Is it bad? Is it something that you had expected before? Is it something that was totally unexpected and now someone needs to set up a new theory because your observations do not match with any formulas? Of course, can be also a measurement error, something like this. So that's the general idea of writing protocols. Okay, so now we can already come to a question, how to do this? Hello. And for most protocols that you write in a university, for laboratory internships and stuff, there's kind of a strict structure. So there's usually a cover page, then there's some theoretical fundamentals where you explain the formula, the necessary theory, state of the art that some educated reader in the field would need to know in advance to understand what you have done. Maybe there's some part about the preparation of the experiment. Then, of course, the procedure, this will be the main part. Yeah, so what have you done? What was the outcome? And so on, the results. Then, especially during this theoretical fundamentals, you will use sources that already exist. You won't come up with too many new formulas. So you need to cite these sources, put them in some list of references. Maybe there's some declaration of authorship, and maybe you have to append your original handwritten notes with the signature of the supervisor or so as an appendix, maybe not. I mean, this depends on your laboratory internship. On the cover page, there's usually a template, stick to this template. All the necessary information should be given there, and it should be complete. I mean, that's more or less it. Then for the theoretical fundamentals, this a little bit depends. As said, it should be what should a person that has general knowledge, let's say in mechatronics or in electrical engineering or in process engineering, would need to additionally know to understand what you have done. So if it's something about filters, maybe it's necessary to once again explain what the filter is, how to measure attenuation of a filter, what the filtering structure looks like, and so on. And give the sources for this. Usually it should not be something in this length range of 1 to a couple of pages is usually okay. I mean, you should not write a book there. So it should not be too general, too broad. It should not be also too detailed. You don't need to give all the detailed derivation of all the formulas. And usually it's not a good idea to copy from the instructions of the laboratory task sheet, because this is what your supervisor knows, or this is what shall be known in the field, I would say. So then for the preparation, this is maybe also something that you have to do in advance. So do it timely. Just stick to the manual, stick to the instructions. Don't be too creative in solving this task. And as with writing LaTeX documents, if things are getting complicated, then you're somehow doing it wrong. It should not be rocket science. You should not reinvent the wheel there. It should be just that you don't totally come unprepared to the experiment, to the day of the experiment, and then in the laboratory starting to read the instructions. The idea of this preparational task is you should read the instructions before, understand them, and somehow go prepared to the day, to the lab, and so on. I also had a very strict supervisor that I remember. I don't know if he's still working at the university when I studied. And of course, we also had usually some tests in advance where he would ask some questions to check if the students are prepared. And so he was very strict, but he could not be bad to students, let's say. He could like, yeah, you are badly prepared, go home again and prepare and come again better prepared. So if you would attend badly prepared to the experiment and he would notice that you are not well prepared, then he would shortly go out of the room, come in again and would say, maybe, so if we would have met today and if we both had the impression that the day is not a good day today to do the experiment, so then maybe you should find another day to do it. Yeah, so if there are some preparation tasks, prepare. So then for the experimental procedure, I mean, we will take a look at this a bit later. If there are some subtasks like A, B, C, D and so on, stick to this. Use some introductory and transitioning sentences. And in the next section, we will explain, or this and this will be explained, and so on. Give mathematical equations, numbers, units, and so on correctly. Then usually equations, figures, tables should be numbered. Why should such things be numbered? Why does every figure, every equation, every table usually gets a number? Yeah, to easily find it and to refer to it, to say this and this is shown in figure 1. Now we take the result of equation 2 and insert it into equation 5. Yeah, otherwise it would be very complicated. And the problem with figures and tables is that figures and tables usually are inserted as floating objects in this document. And this is always a bit difficult to explain, so I need to, I don't know, do I have some paper somewhere? Yeah, maybe. Yeah, difficult to say. I just have a small piece of paper. But imagine like this is one page. Maybe I can go to full view with my camera for a moment. Imagine this is one page of your report, of your protocol. And you have some text already. Or maybe you have already like this much of text, and now you want to insert a figure of this size. And of course, the figure would not fit on this page anymore. So the figure would go to the next page. But then you would have some blank space here. So what a good document typesetting system like LaTeX does is it takes text from the next page and moves the text to here so that you don't have white space, but the figure goes to the next page. Or the figure can also sometimes move up to the top of this page. So figures and tables, as said, are floating objects. And that's why you cannot say in the following figure or in the previous table, because the figure does not necessarily need to follow or need to be prior to the text where it's written. That's why it's necessary to number them and try to remain accurate. Yeah, and for the discussion, as already said, it's especially interesting if you discuss what you would not expect before, what some anomalies, some uncertainties, also maybe what is not so perfect on your measurement setup, how could it be improved, how could you improve the precision of the results, something like this, the accuracy, and so on. What are sources of errors and so on. So then if you cite sources, every reference, every source that you cite should have an author. And the author could also be an institution like some standardization body or like the Wikipedia. I mean, we can discuss in a moment if Wikipedia is a good source, but there should be some author. Then every source has a title, some name that is on top of the source. Then every source has a year or a date when it was published so that others can see, is this some recent source, is this the very old source, how old is it? And there should be some way to access the source. This is the fourth one. So usually now we have lots of electronic sources, so there's some URL, Unified Resource Locator, or some digital object identifier, DOI, and for classical books you would give a publisher that published this book, for example. Yeah, and so there are some examples here how this could look like, and these examples are also in the same way sources that you could also refer to when trying to find some more information on how to write papers, protocols, and stuff. This book here from Springer, this is something that you can access via our university library for free if you are inside the university network. And as you can see, it's from a German couple, Lutz and Heike Hering, about how to write technical reports. And the interesting thing is that this book also exists in German, because they have at first written it in German and then translated it into English. So it's a quite well-known book in German, but it's also readable for the international students, which is, from my point of view, very good. And so then how to cite this in terms of, for example, that here the author names are written in Roman type upright letters, the title is written in italics in these slanted letters, and so on. There are lots of styles out there how to do this, and there's kind of a sport, I would say, almost, that every chair, every institute, every laboratory supervisor kind of invents his or her own style to do this. I would, so for German documents, there's a DIN norm from Deutsches Institut für Normung for this, so I would always stick to this DIN norm, and if someone comes up with a different style, I would ask, hey, we are living in Germany, why don't we stick to this DIN norm? And for English documents, I would always use this IEEE style, because IEEE is the main, or let's say one of the main publishers for scientific documents, papers, and so on in international things. So why not refer to this style? So this is what I would recommend, and you will find this style in, I would say, in most of the programs that are out there. Okay, so yeah, then we had the question, is Wikipedia a good source? Some people are doing like this, no. I've seen some people that say yes, maybe. I would say, as usual, the engineering answer is it depends. So I mean, I'm not too much into political sciences and so on. From my point of view, it can be questionable there, but for let's say the hard sciences, mathematics, natural sciences, engineering, from my point of view, it's a quite good source, because people do mistakes. I've read lots of books, and also books sometimes contain horrible mistakes. The problem is no one will correct the book. Yeah, the author of the book does not drive around and say, hey, you have bought my book 10 years ago. I noticed that there's a mistake on page 125. Can I please have your copy and correct the mistake? I mean, sometimes, of course, there's a new edition and errors also get corrected in books, but chances are still rather high that yeah, there are mistakes in books, no one will correct them. Chances are pretty high that if there are mistakes in Wikipedia articles, people will correct them. I have also corrected lots of mistakes in Wikipedia articles, and so from my point of view, this is quite good. Of course, Wikipedia articles also usually refer to other sources, and then you can check back what is written there if you are unsure. But yeah, I would still say in engineering and technical sciences and so on, Wikipedia is a quite good source. And on our website, maybe I can go to this for a second. So this is the German page, but there should be also an English translation here. So we also give some guidelines and templates for thesis. There's a German, there's some English version, and you can also check this document. There's more information about this there, how to properly cite sources, and also, for example, what is a direct citation, what is an indirect citation, how to avoid plagiarism, and so on. Okay, so in the appendix, maybe as said, scanned handwritten notes. Just make sure if you scan or do a photograph of them that the resolution, contrast, and so on is good, and everything is well readable. Okay, then we can have a look at the style, and as we already said, that a degree thesis is something like a large protocol. A protocol is something like a small degree thesis, so why not use the same style for this? And once again, you can refer to this guidance on the preparation of degree thesis that you find on the website of our chair that I just mentioned. Okay, and so now we can take a look at some details. If you, and this will happen very frequently, if you put diagrams, plots, schematics, something like this into your protocol. So example here is our mains grid voltage, right, that comes out of the power outlet. There's a clear axis labeling, that the numbers are well readable, that there's maybe a grid to check if this zero crossing here is really exactly at 10 milliseconds, for example, and if there's more than one curve, there should of course be also a legend. And then what I've not explicitly mentioned here, what from my point of view is also very important, is to use the correct file format or data format for such figures. And what is a good file format or data format for such figure files or for such schematics, plots, and so on? It's vector graphics. And we will see raster graphics later on, but vector graphics are graphics that consist from single basic geometric elements like lines and of course letters and stuff, but the advantage of such vector graphics is if I arbitrarily zoom in somewhere, you can see that it will always look good and nice. You don't see single pixels. I mean, there's some artifacts here, I think, that are some problem of my PDF reader here. But yeah, this is for sure the advantage of vector graphics, that they are scalable without loss of quality. So you can show them very small, you can show them very large, you can print them on a small sheet of paper, you can print them on a poster, they will always look good. Okay. Same is for tables. Clear mentioning of the quantities and the units that are given there, nice number format, and tables should be also inserted really as tables and not as a picture of a table, which also sometimes happens, unfortunately. So then diagrams and tables get captions. Interestingly, and we can also discuss this, figures get captions below the figure, tables get captions above the table. Why is this? Because tables can be also longer, sometimes longer than one page, and it would be kind of stupid if you have table, and then the caption, the description of the table follows behind the table. And figures are usually not that long, that's why figures get the caption below the figure, tables get the caption above the figure. And they should be self-contained and understandable, so they should be better too long than too short. Why is this? Because, I mean, just look at yourself. If you're reading something, like you're reading a book, you're reading a thesis, a document, a paper, if you don't have much time, what do? You skip through the pages, you look at the figures, and you try to get some idea what has been done in this work just by looking at the figures. So figures should be good and should be understandable by themselves, because they are kind of the figureheads of your document, the first-class citizens. The figures will be the things that other people will look at first when reading through your document. Okay, so with these references we already discussed, and what's really bad is raster graphics and JPEG compression, because this JPEG compression is a lossy compression. It creates additional compression artifacts, and they just don't look nice. I think we will have some examples later on. Because this JPEG, I mean, by the way, you're probably using JPEG compression every day, right? Because if you do a picture with a smartphone, it will be saved in this format. Does anyone know what this abbreviation JPEG stands for? There's one.
Joint Photographic Expert Group.
Excellent, exactly. Our Joint Picture Experts Group. So it was a group of experts that developed this picture format somewhere in the, I don't know, 1980s or early 1990s or something like this. And does anyone approximately know how it works? So you know from electrical engineering some Fourier series or Fourier transform. So the idea there is the picture is a two-dimensional function, because you have like grayscale values in x and y direction or color values in x and y direction. So you have a two-dimensional function and you do a two-dimensional Fourier transform of this picture and you save the spectrum. And if you would save the whole spectrum, it would be totally precise, no problem, but then you would not save anything. So the compression happens in a simplified way by throwing away the high frequency information. And the high frequency information are the rapid changes in the picture. And that's why if you compress something with a JPEG compression, and if you have this strong contrast going from white to black and so on, always there you get this compression artifacts, because this is at the end, this is like Gibbs ringing that you have in the Fourier series. So don't use JPEG compression for figures, plots, and so on. This is looking really, really bad. Okay, so then I have just listed some further hints. If you use abbreviations, especially if you're not common, please introduce them. Only introduce them once. Don't introduce them. Don't explain them on every, because then you don't save any space by using abbreviations. The same is for variables. If you write down a formula, if you use some variables, some symbols, explain them. What do they mean? If you have these references, something is shown. You can also, in figure 1 or on table 2, in equation 3, whatever, you can also refer to other sections. And if some reference is, you refer to a figure that was already 10 pages ago, then it's also sometimes nice to say on figure 2, on page 3, because then people know on which page to look for this figure. So then this is now already getting quite sophisticated. If you say figure 1, table 2, page 3, whatsoever, this number should not go to the next line alone if this happens to be at the end of the line at the line break. So between figure and the number, there should be some non-breaking space. There's some nice Wikipedia article that explains how to get non-breaking spaces in different document editing things. So you can check there how to do this. Then if you, I don't know, introduce something in a sentence like a different thought, you use a hyphen. If you break up words, you use a dash. So be sure which one, this longer hyphen versus shorter. No, I think I've actually done it wrong. The hyphen is the short one, the dash is the longer one. I'm sorry for this. This is something that should be corrected. No references at footnotes, but references at the end in the literature section. And if you give circuit schematics, use the existing symbols. Don't invent your own ones, because this is confusing people. So there's a nice list of electronic symbols, I think, where they are all explained. So just stick to these standards that are given in different sources. So then what I sometimes see, especially with international students, is that it happens that there is no space behind the comma, or that there is no space before opening parentheses, or no space behind the period, and there should be a space. So there it's like clamped together. That's why there is this word, this is called a clamp. And what I also sometimes see is the opposite, and the opposite is called a plank. This is this one here, or this space. So here there should be a space, here should be a space, here should be a space, but there should be no space. Here should be no space before the period or before the comma. And there was some English Wikipedia article that explained this. I think this unfortunately got deleted a year ago or so, so you have to refer to the German one. But there are also nice examples on this German one. Like here, this space should not be there, or I think here, some old street sign where the comma is just misplaced at the wrong position. Okay. So then for mathematical formulas, I mean, there are lots of rules for formatting, so we could talk for hours just about mathematical formulas. Does anyone recognize what this formula means? Laplace transform or Fourier transformation. So this is what you would need to use for this, also for this JPEG transform, but with 2 dimensions, not just with time. Yeah, and so the idea there is you need to use a formula editor. And the best way to do it, once again, is to do it in LaTeX. At the end, you can also do it with MathType or MathML. There are different languages, but you need to use a good formula editor. And think about, so as said, we could talk about this for hours. Think about style, sizes, spacing. One mistake that I often see is that people, for example, say, hey, we want to have a function like here, or our spectrum as a function of angular frequency, for example, divided by some normalization quantity, and then these parentheses that should enclose this are just too small. So here they would have, let's say, the right size, the perfect size. Here they are already a bit large. So yeah, think about this. If you write many formulas, you will get some kind of awareness for this, what to check for. The analogon of this is, yeah, if you have too large content, too small parentheses, or if you have too large parentheses, too small content, it's the same problem with the hot dogs here as with the mathematical formulas. Okay, so then if you write formulas, and if you do engineering sciences, you will also write units. Mathematicians don't care about units, but engineers do. And there's a nice brochure called the SI brochure. SI stands for System International, the International Unit System. I'm sorry, my French pronunciation is very bad because I learned Russian in school. Of the, yeah, Bureau International Points and Measures, so the International Bureau of Measurement, and I don't know what the English translation is. So, but they have a nice brochure. You can also find this on the internet. And the main rule, or there are some main rules. The first rule is units are always written in upright letters. So not slanted, no italics, upright, Roman type. And so this also applies to other mathematical quantities as well. So for example, if you have some index, like you have a voltage and it's the maximum voltage, then maximum is a word, or is the abbreviation for maximum. And because it's not a symbol, it's not a variable, because it's a word, it's an abbreviation, you would also write this upright. The volt is also written upright. This would be wrong, this would be wrong. So then functions with a special meaning, like the sine function, cosine function, and so on, they are also written upright, not slanted. The E here is not some arbitrary E, it's Euler's constant, it's a fixed constant, it's 2.71, I don't know, 2.7 something. So it's a special number, it's a fixed constant, it's written upright. Also the df to dx, the d is not some arbitrary variable d, it's some operator. It's a differential operator that calculates the derivation of some function, or the derivative of some function. So this is also written upright. Then there should be a space between the number and the unit, can also be a thin space. And it should also be a non-breaking space, so there should not be the number at the end of the line and then the unit following at the beginning of the next line. You can try to use a consistent format, so decide for this or for this, for example. Giving units in brackets is usually wrong, and try to use a nice number format for the scientific notation like this with the power of 10, not this, what would be the output of if you use MATLAB or Octave or Python or whatnot for your calculation. Why is this important? Because if you don't stick to these rules, people will not understand your formulas, because same symbols have different meanings if they are written in a different way. The upright M is the meter, the slanted M is the mass. And there are other things like this where it really depends on the style what this at the end really means. Okay, so then we can have a look at software. And so here I have a next question. I need to find this one here in my question set. So this should be this one here, and I will now set 1 minute and repeat, and there's the QR code. And so the question is, which word processing software do you currently use to write protocols and stuff? And we already have 20 answers and something like 20 seconds left. But there's still some smartphone pointing at me, so I will still show the QR code. And so the options were Microsoft Word, something like OpenOffice or LibreOffice, LaTeX, also online, maybe on Share LaTeX or on Overleaf, Scientific Workplace, or something different. And so once again, the blue results are the current results, the light blue ones are the ones from last year. So lots of people using Word, only one person I think using OpenOffice, some using LaTeX, and some using something different. Who has selected something different? What would be something different? I could imagine something like Google Docs, for example. Okay. Yeah, so I think here I've also written down Google Docs or Collabora Online. Okay, my opinion is very clear. Microsoft Word is a nice software to, I don't know, write a letter, maybe write a couple of pages of text, but not for scientific documents. I mean, it's just not made for this purpose. There are lots of memes about this. I think you will see some more in the presentation. And I think the problem is intrinsically related into the software, because it's this is what this abbreviation stands for. It's a what you see is what you get software. And if you want to write good scientific documents, from my point of view, you need to separate content from style. Yeah, you want to write, for example, this is a vector, and at a different place, a vector is displayed by a bold-faced letter, or a vector is displayed with some small arrow on top or something like this. Yeah, but you don't want to mix this up. And this is done in this kind of software here. And that's why documents written in software like this are often not that good, because style then gets mixed up throughout the document. So then there are systems like LaTeX. So on Windows you could use MikTeX, on Linux you could use TeXlive. If you just have a browser, you could use Overleaf, which is not mentioned here. And I mean, this is really separating content from style, and you kind of program the documents, which can be hard at the beginning. I mean, that's why we have this introduction to LaTeX workshop in the next week. And there's something in between that is called What You See is What You Mean. There was a software called Scientific Word. I think it can be still downloaded for free, but the company that developed it somehow discontinued it. And there was something, for example, called Lux. I think this is still being developed. this is some kind of software. They use LaTeX in the background, but still you get some kind of nicer editor to write your documents. So if you're, let's say, just starting, and if LaTeX looks too complicated for you, this may be something, would be maybe something interesting to have a look at. Yeah, still, what happens often in Word is documents get confused. There's another meme, another joke explaining this problem. And the problem, yeah, and I think the issue there is that there is not just one word. Especially if you collaborate with many people, one person has this version, another person has this version, then documents just get confused and will somehow break. Then, this is a nice XKCD comic. This is, by the way, also a very nice website with lots of engineering jokes and humor. Yeah, a nice chart that convinces engineers and scientists the trustworthiness of information by file extension. There's, of course, the TeX file on the very top of this charts. The doc is somewhere in the middle, and at the bottom you see JPEG and the GIF or GIF format. So, yeah, TeX is the way to go. Then to create figures, I've just mentioned some software here that is interesting from my point of view. This Dia is a software to draw these vector graphics and to export them. This IPE is something similar. Here you have the advantage that you can directly, for example, also insert LaTeX source code for the labels, so that at the end the labels will have the same font, the same style, and so on as your remaining document. This Inkscape, I don't know if someone knows this, is a very generous software to manipulate and to edit vector graphics. And for photographs, I can recommend this XNView, which is also some kind of free software that I use, I don't know, to adjust the contrast, the brightness of figures, to maybe crop them, and do stuff like this. I mean, it's not really sophisticated photo editing software, but for the basic stuff, and then it's doable, and then it's kind of easy to use. Yeah, if you need to rotate a figure, flip it, do stuff like this. And for LaTeX users, I've just listed some useful packages here. This hyperref package is something that can be used to get links in documents, like the links that I've shown you, that will open up in a browser. AMS is the American Mathematical Society. They have a very nice package to typeset formulas. This SI-UnitX is for units, right, for the System International. Then the two packages that I've printed here in boldface letters are ones that we will take a look at the tips section. And TIX, yeah, so this is something for diagrams, this is something for circuit schematics, and it's based on this TIX. And TIX is a stupid acronym for TIX is kein Zeichenprogramm. TIX is not a drawing program, and I mean, at the end you can use this to draw figures in LaTeX. Yeah, and there are lots of packages for this. So just some introduction and some useful editors. I think nowadays most people would just use Overleaf, do it online for smaller documents. This is the way to go. And yeah, don't use Word for too many, or for documents with too many pages and too many figures, because if you have done so, you will have observed this for yourself. Maybe, I see some people nodding, and yeah, this has happened. This is what unfortunately happens there. Okay, then we can have a look at some good and bad examples. And these first examples here, they are somehow related to style, and the second row of examples are somehow related to content. And if you take a look at this, I know it's in German, but it's not really about the content. So what comes to your mind if you take a look at this example here?
There is no alignment.
There's no alignment. Usually for documents with more text, you would use this block quotation, so that every line starts and ends at the very same position. But I think this is a minor problem here. What is probably the major problem in this example?
There is no paragraphs.
Yeah.
There is no spacing, it's like very hard to read.
It's kind of hard to read because there's no spacing and there's no indent. And are there other ideas? There's one. The font size is the same each and everywhere, right? I mean, this should be a main heading or the main title of the experiment. This should be like a section. This should be probably something like a subsection, another subsection, and so on. And here we have the second section. And for each and everything, just the same font is used, which is kind of stupid. So the same thing looks much better and much easier to read. And as you mentioned, now we also have some spacing. And we have different font sizes and different font style for the different parts inside the document. Second example, what happened here? So Inhaltsverzeichnis means table of contents. There's no dots. So usually you would have something like that. It's the number, the section, some dots, and then the pages would be all on this side. And this is some nice example that you can also do it horribly wrong in LaTeX if you don't really understand how LaTeX works. Because what happened here is I think that the persons who wrote this, they have manually created this table of contents. But there is one command which is called table of contents, and this will automatically create you a table of contents. And if you do it in this automated way, it will look like this, right? And it will look much better because here we have this indent, and here we have these dots, and here we have all the page numbers on this side and so on. Okay. So then I have a third example related to style. What's the problem here? Or what are the problems here? Because it's not just one.
Like a screenshot.
It's a screenshot. It's a screenshot from MATLAB because you can see it from the gray background. And it's a raster graphic. And if I zoom in here, you can also nicely see these JPEG compression artifacts and how it's looking really, really ugly when zooming in. So yeah, it's a raster graphic. It's formatted, or it's saved in JPEG. What else? Yeah, the axis labels, then person notice, oh, damn, I forgot about the axis labels. So axis labels have been added subsequently. Then maybe the grid is missing. I mean, this is in the paper report, it might be okay. Now for the presentation, the font size is a bit small. Yeah, so there are many things, many issues with this figure. If we would take the same data and now, for example, replot it directly in LaTeX using this PGF plots package, it would or could look like this. And so now you can see now it's a vector graphic. I can zoom in. It will always look good. There are nice clear labels. There's a grid and so on. Okay, and as example, it's very. I think it's very probably a JPEG also. Yeah, I don't know if there was a title for this, but this is just super bad style. I mean, this was probably created with the motto, Microsoft Paint is your friend. Yeah, and then something has been drawn, then this has been rescaled, then some other elements, because here this looks much sharper, for example, than this one. Some numbers, yeah. Also, what is this here? It's not even readable. So this is just really, really bad. I mean, this is there is so much wrong here. It's really challenging to explain. And so this will be one of the other examples. If you would use circuitics, for example, in LaTeX to recreate this, it would look like this. And everything is nice and readable. It's a vector graphic. You can zoom in. It will always look nice. It looks much better. Okay, so then we can have a look at some examples that are now more related to the content. So here we have a list of figures. What maybe could be improved related to this list of figures? I would say this is okay. I mean, this was measured. I would maybe insert for a frequency of f equals something like this and this in megahertz. I think this is probably okay. I'm looking at this here because what is listed in a list or summarized in a list of figures are the figure captions. And so now imagine you have a figure, and below the figure there it says figure 3.5 or so, figure showing the experimental measurement. I mean, of course a figure is showing something, I know, and the graph is also showing something. So this is just redundant, and yeah, the experimental measurement, the measurement I would say is always experimental, but what type of, so there is something here, but this is not saying anything at all. Yeah, so I don't know, at least this figure showing, I would cut this and just say experimental results, and then maybe, I don't know, for the resonance curve or something like this, that more explains what is happening there. And then what might be even better is to have one figure with experimental results for this measurement curves, and then have 3 sub-figures for the different frequencies, for example. Yeah, this would also remove some redundancy here in these figure captions, in this list of figures. This is also a very nice example. So as you can see, this is some screenshot from some oscilloscope measurement from some Tektronix device, and the figure caption is, it's the oscillogram to measure the periodic time using markers. So you are all engineers, maybe not all electrical engineers, because we also have some process engineers, but now I'm giving you, I don't know, 30 seconds to take a look at this diagram, and I will ask you, what is the periodic time? You had a different comment? Sort of? Okay, explain, the others can think about the periodic time. Because this was the idea of this measurement, to show the periodic time using markers. So what is the periodic time? Who has an idea?
2.4 milliseconds.
2.4 milliseconds? I don't think so.
Actually, the scale is not mentioned.
Yeah, so there are some markers, and there's a scale somewhere mentioned, but no one really knows. So from my point of view, we have the 200 microseconds here and with the 200 microseconds there. And the 200 microseconds is the time per division. And usually you have 10 divisions along the x-axis or along the time axis on the oscilloscope screen. So going from here to here, this is 200 microseconds, another 200 microseconds, and here we have one full period of time and another 100 microseconds then. So the full periodic time going from here to here over one period would be 500 microseconds, 0.5 milliseconds. And the corresponding frequency, if you calculate the frequency, 0.5 milliseconds periodic time, you would end up with 2 kilohertz. And the 2 kilohertz is the thing that is mentioned here. Because we have a marker here and we have a marker here. And so the delta frequency marker between these two, which is one full period of time, would correspond to 2 kilohertz. So it's from, let's say, from the style. It's a nice screenshot, everything okay, but no one will get what is the periodic time from this. It's really, yeah, so we had now 20 people in a room staring at this for a minute. No one would come up with a good answer what the periodic time is in this case. So the problem then is no one will understand. Yeah, so the message, the idea of this figure here is to deliver the information, what is the periodic time that has been measured, but no one will get this message. No one will understand it. And in this case, it's a bad figure. Yeah, so, and then there are some other improvement opportunities. But okay, so then, yeah, I think this is the last example. This is something that probably needs some time to read. So I will give you some time to look at this, and then you can have some comments what is maybe wrong here and how it can be improved. Exactly. So the first thing is this formula, this equation should be numbered. Other things.
The units of measurement should be in the equation.
The units should not be inside the equation. Exactly. So here, interestingly, this equation is numbered, but the numbering of the equation should be aligned to the left. Yeah, and I mean, then if I zoom in a little bit, yeah, so this is a dash. Here it's just a hyphen. Here there is a space. Here there's no space. Here there's nothing at all. Yeah, this is like a full sentence, but this is just a head word and so on. So, yeah, the style is not that perfect. And so what we could do is to write it as full sentences and to say where omega is the angular frequency, u is the energy stored, and so on, properly number this in this equation and just have this in sentences, or maybe do it like this and say where omega is the angular frequency, this is the energy stored, this is the average dissipated power. And for example, because the D here is the abbreviation for dissipated, this should be typeset in a Roman type letter, in an upright letter, not in a slanted letter. But everything else are variables, so they should be slanted. Okay, so once again, it's much easier to do it right in LaTeX. It's much easier to do it wrong in Word. I don't say that you cannot write such documents in Word, but from my point of view, and you don't have less or more problems. In LaTeX, you just have different problems. And you don't need more or less time, but still, I think at the end, you get the better result when using LaTeX. Okay, so there's the last poll and question, and I need to find this on the page here. No, I think it's not the last one. So we can try to repeat this, and there's the QR code. And the question is, why are you not using LaTeX, or what was before maybe the biggest hurdle in using it? And while you are answering this question, I will try to fix my preview window here because my laptop obviously has no Wi-Fi anymore. Okay, so that's the result. And most people say, I was just not aware of it. And some people say it's too complicated and too much like programming. And unfortunately, the label here is not nicely shown. What is the other? Too time consuming, too shallow learning curve. Yeah, maybe. And it's only used in academics, not in the industry. This is partly true, but I mean, it's up to you to change this because it's a free software, it's very powerful. And I think the main reason why in the industry it's not used, it's because we have always used Word, so why use something else? Okay, so now we can have a look at some tips in LaTeX. And the first example that I would like to explain is how to draw a diagram with PGF plots. So this is how the corresponding LaTeX source code looks like. And the idea here is if you understand how to plot something in MATLAB, you might also understand this here. So we have some environment that is called this TIX picture. This is the general environment to draw figures. And then there is some axis. An axis means now this is getting a plot. This is becoming a diagram. And this is linear axis. There would be also log axis, semi-log y-axis, semi-log x-axis, and so on for logarithmic scaling. And then we, into this environment, we add some plot. And we use a formula. So here we are using some sinusoidal function multiplied with the square root of 2 and 230 volts. And we take this 2 times p times x divided by 20 because we divide by the periodic time of our main grid voltage, 50 Hertz, we have 20 milliseconds. And then we plot it over 20 milliseconds with 101 samples. And so the outcome of this is the source code in LaTeX, and this will create this diagram. So we get numbers on the axis, and we get this nice curve, and this curve now consists of this 101 points that have been calculated according to this formula. Instead of this formula, you could also write values directly into the source code, or you could also load a table with values. Formula is just the simplest case for my demo here. Okay, so then the next step, of course, would be to make it a nice diagram. We need to label our axis. So we add some x label and some y label, and can say this is something with this symbol and this unit, and if we do this, we get nice labels. And now you also, you maybe already see the magic of this, because here we just give the content. And the style is defined somewhere else. And so in the presentation is also created in LaTeX, of course. And in presentations, you would usually use such sans serif font, a font without serifs, like an Arial font or Helvetica font, because you don't have many words on the slide, so it's easier to read in this case. And so that's why it will also use a font like this here for my axis labels. In the document, in the paper, in the protocol, you would often use a serif font, like in a book. Yeah, and serifs are these small, like here, the small things at these letters, like in this math font here, and they would help our human eye in reading line by line by line in a longer document and book. And so if you would take this figure use this source code, put it into your protocol, it would automatically adapt to the different font. And this is really, really the big advantage, one powerful advantage of LaTeX. And of course, if you want to change these labels later on, if you want to translate them, whatever, you can directly do it in the document. You don't need to go back to MATLAB, to Octave, to Python or so to replot the diagram with different labels. Okay, so what else could we do? We could, for example, have a second line, or we could rescale the diagram. So here I think the first thing that I have done is let's get rid of this space here and there. So I've changed the axis limits so that the x-axis really starts at 0, ends at 20, and the y-axis at minus and plus 250. And so then the diagram looks like this. So what we could do is now we can change the size and say, for example, our figure, our plot, our diagram should be wider. And so then it's getting wider. And it will automatically, because now there is more space, it will automatically add more numbers. If you have created a figure in MATLAB, a figure in Octave, you cannot later on rescale it so easily. It will always, the font will then get too small or the font will get too large, and you cannot rescale one axis because then it looks like if you if you would have created this figure in MATLAB and then changed the aspect ratio to this wider format, then also the letters would get wider and so on. It would look bad. So this is really, really powerful from my point of view. Yeah? And so then we could add a second plot or not a second plot, a second line into this plot, and add a cosine function to the existing sine function. And because we have two lines, we also need to have a legend entry for the first one and to have a legend entry for the second one. And then final result, for example, would look like this. And okay, this is somehow looking complicated, but every line is quite simple, and still at the end you get a very nice result. Yeah, and the easier you learn this, the more understandable it will be. And so here it's very easy to adapt things later on. It's a very powerful format. So as already mentioned, you can get data not only from formulas, but also from tables or directly specify them. And you can not only do these line plots, you can also do scatter plots. You could do something like bar charts, comp and quiver plots, polar coordinates, stuff like this. And you could also do, you can more or less do everything that you could also do in MATLAB or Matplotlib or in any other powerful plotting program. And yeah, this is, of course, a strong advantage of this LaTeX typesetting system. You see I do lots of advertisement for this. And once again, in Word you can ruin everything by moving a single image. Okay, then let me quickly close the door because there's some noise outside. But it's not getting better. Then the second example that we can have a look at is this circuit schematic. And for the circuit schematic, I think to explain this, I usually use the blackboard, but this was not that powerful, so I will try to do something else and use my not hour but journal. And paste this here. So this is the source code, and so now I will start my drawing tablet. And it's luckily already connected to my computer, so I can use a pen here and draw something. And to understand what happens here, you need to think about a coordinate system. So let's have a vertical axis, a y-axis, and some horizontal axis, some x-axis. So x and y. And now inside this coordinate system, we draw points. So the first thing here is always the x coordinate, and the second thing is always the y coordinate. And so let's say that here is 0 and 0 on both axes. So the first point that we would be starting at, this point here would be this one. This would be the 0.0 point. Okay, so then from this point to the next point, we are drawing some I is a current source. And x0 we already know is here. Let's say here is 2, here is 4. So the next point, which would be this point here, is here at 0.4. And between these points, I will try to use many colors. Between these points, we are drawing some current source. So this gives the current source. Then we have the next point, which is 4.4. And the 4.4 point should be somewhere here. Because here is the x-coordinate 4, here should be 2 somewhere in the center. And I'm already running out of colors a bit. The yellow thing is not that visible, it's okay. Yeah, so we have a short connection to this point. Then to the next point, which is this one here at 4.2 or 4,2. We write or we draw a variable resistor. So from here to here we get a variable resistor. And to the next point, you get the idea, right? So we have coordinates, and between these, or in between these coordinates, we have the elements. And so we would get another resistor going down here, and then we would have one short connection back. Maybe I can draw this, because for this I have enough colors. So one remaining resistor, and then one short connection going back to the origin. So this would be the short going back here to the origin. And that's why this source code creates this figure, like what I've just drawn here in my program. The current source, the variable resistor, the resistor, and 2 short connections in between. So then we can add the inner branches in the circuit, have another variable resistor, have another resistor, and another resistor, let's say horizontal. So this would be vertical elements. Oops. So we would get another variable resistor, and this is the horizontal resistor. Okay, does not look too bad. So next step is we need to have labels. So for each element, for the variable resistor and for the resistor, we add some labels saying, hey, this is the resistor R2, and this has 1000 ohm, and the next one has 820 ohm, and so on. So we get these labels. And then we see, oops, what's the problem? There's not enough space for the labels. We get some overprinting. So what could we do to get rid of this problem?
Vertical?
Say again?
Label vertical?
We could have the label vertical, but vertical labels are always challenging to read. Another idea? Yeah, we could make the label smaller, or we could make the figure or the schematic in itself larger. And okay, making the labels smaller, then it will be difficult to read if the font size is getting too small. So, and we have enough space here on the slide, so just let's make the figure larger. And okay, one idea to make the figure larger would be we would need to change the 4 into an 8, for example, and so on. Yeah, we would need to scale everything in the x direction, for example, by a factor of 2. And this is also very easy because there is some, we leave all the coordinates as they are, and we really just change the scale. Blow up the x scale by 1.6, blow up the y scale by a factor of 1.2, and then, so I've just changed this here, I've just added this. I've just added the scaling here, and so then the figure looks like this. Okay, what is still missing probably on this circuit schematic? Yeah, the labeling of the current source and these soldering dots here that show that these lines are really here at these branch points or nodal points connected to each other. So this is added by this here. So at the beginning of this, we would have to have a full dot at the end of this element, and at the beginning and the end of the horizontal element, we would need to we would like to have dots, and then we would have a label here also for the current source. And then it looks like this. And I think I've also added some more current labels here for these different elements and resistors. So very nice schematic now. And once again, it's a vector graphic. We can zoom in and out. It will always look good. Okay, so further options for this package. So now we have just used bipoles that have a beginning and end. There are also monopoles like a round symbol or some antenna. There are also tripoles like a transistor, or double bipoles like a transformer or coupler or something like this. And you can also use this concept of separating content and style also for the circuit schematics. So you can have European versus American style for the circuit symbols. And so you can have a long document with tens and hundreds of circuit schematics, and you change one line in the document, namely American resistors instead of European resistors, and then all the circuit schematics in all your document will turn from these resistors into these resistors. And this is of course this gives people a feeling of power, right? Money status is nice, but using TIX and LaTeX, this is really what makes you happy. So coming to the last poll, what LaTeX related topics would you like to see in future workshops? And I need to open this up, and I think it's this one here, and then I will just repeat it with 45 seconds, and there's the QR code. And then I will pass this to my colleagues for the other workshops, and then they might put some more emphasis on these special topics. So the choice is typesetting formulas, typesetting tables, citing sources and listing references, drawing schematics, for example, of measurement setups or flow charts of programs, something like this, or creating presentation slides like the one I had. And for the persons who say, don't bother me with LaTeX, I've also had this option, but this is only what one person has chosen. And I think the winner is typesetting formulas and drawing other schematics. So I think the formula stuff will be in the basic workshop, and then if we would check the student branch website, there will be another workshop especially related to figures and graphics in LaTeX. So this, I think, somehow makes sense. Okay, so to summarize, if you write a protocol, one main rule is also the advisor of the laboratory or the lab internship, the lab course, should see that you somehow have cared about writing the protocol. That it's not something that you quickly coming back from the bar last night before going to bed, you have done very quickly, but that you tried hard and you took care to prepare this protocol. And I mean, we can ask the German students if they agree or not. I also, when I studied in Magdeburg electrical engineering, it's still on a diploma course, to be honest, of course, I also hated writing protocols because it consumes lots of time and it can be really annoying. So, but the thing is, what you don't see at this time is that you really learn a lot and that you collect lots of experience and gain lots of knowledge in writing such technical documents, and that you are already very, very experienced when you are writing your bachelor thesis or your master thesis, or at my time of study, the diploma thesis. And so if you would not write all these protocols, then you would have much more burden and much more pressure and much more difficulties in writing the degree thesis because you don't have collected this knowledge already. Yeah, so coming back to this, the degree thesis that you write is also just a large protocol. If you have properly understood how to write the protocol, it will be way, way, way easier to write also a degree thesis. And that's why, yeah, I also did not like it. It consumes lots of time. But see it from this point of view. It also has some advantages. And so you have also already written your bachelor thesis, right? No, not yet. Okay, you're okay. Yeah. And LaTeX is a powerful tool, but you also need to learn it and you need to get acquainted to it. And this chart tells it pretty well, right? If you start with something, it's very easy to start with Word. But the pain grows the more pages you have, and the pain grows exponentially. And for LaTeX, you have some initial pain. You need to, if you do it locally, you need to install software on your computer. You need to have like a hello world document. You need to get to know how to run the compiler, how to check the result. Then there will be lots of strange error messages if you just forgot a closing parenthesis, or if there's some semicolon at the wrong position or whatnot. Yeah? So there error messages in LaTeX are also really can be a real pain. So you need to understand these error messages and stuff. But yeah, once you skip maybe this magical line of something like a dozen pages, I would not fix this to exactly 20, but something like this, then it's LaTeX won't care if you have a 2-page, a 20-page, a 200-page, or 2,000-page document. Okay, the 2,000-page document will, no one wants to read this, yeah, but if you later write on a PhD thesis, something like 200 pages in total is not uncommon, with some appendices and with all the stuff. Even if the content is just, let's say, 120 pages, might happen that you have some additional pages for appendices and stuff. So 200 pages is not uncommon. Maybe you will write a book later on. Yeah, there are some books that have more than 200, much more than 200 pages, sometimes it's like 1,000 pages. In LaTeX, no problem. It will just take longer time to compile, but computers today are still quite fast in compiling stuff. And yeah, in Word, you won't get really happy. So try to master this learning curve as early as possible. This would be my sincere recommendation. Finishing this workshop. So thanks for your attention. And we would still have some time for Q&A. I have an IEEE workshop sharply at 5. So, and then I have also another exercise coming. So I don't have too much time for questions, but still we have time for a few questions. And some links that I would show is Maybe you can take a picture of those and try them out later. The examples that I've shown you, the PGF plots diagram and the circuit schematic and circuit ticks, I have these short links here. I will wait a second for the last person to take a photograph. So if you click on this, or if you open this up, it will directly open this example in Overleaf. So you see the LaTeX source code here, you see the result here, and there are some tasks what to do, or what you can try out, some recommendations. Change the height, change the width, remove the cosine waveform, copy the whole plot and change something, change the general setting to a different font and so on. Then you can, and by the way, this is now this serif font here that I'm using in this example. I don't like to change it here and try it out now, because then I would change the template for each and every font. I would need to take a copy first to try this stuff out. But you can find this example here, and you can, and if I open this up, this is just the second example with the circuit schematic. And yeah, you can see it's a quite simple document, this short source code that then creates this example here. And here, interestingly, I've changed it to the American resistors, and you could go back to the European one, for example. Okay, thanks.